Hello. The title of my presentation is Experimental Investigation of Non-Load-Bearing Asymmetric Double-Stooled Wall. This is work developed in collaboration with my colleagues from the Technical University from Paraná, Brazil, and some other colleagues from the University of Rome, Tor Vergata from Italy. My presentation is going to be divided in 7 parts. I will start with a short introduction, then I move to the fire resistance of light steel frame walls. Then I will present some experimental standard tests that we are currently developing as well. And then we move to the numerical simulation, the validation, and present a new solution method, which is called simplified method for this kind of building construction products. At the end, I will do some conclusions. So the light steel frame for non-load-bearing purposes are normally used for partition walls. So it means that this element is not able to sustain or to be loaded, and is normally made with steel sections, cold form steel sections, classified as class 4, and lined with layers of protection that in this case are going to be gypsum plasterboards, and also some can have some insulation inside the cavities. So there are different types of materials for this purpose. The most popular ones are rock wool, but in this case we decided to use ceramic fibers. So the double-stooled light steel frame walls are good for energy efficiency. So in fact, is a very large wall which provides a very good thermal behavior in normal conditions. Normally they are also good for regarding the soundproofing, so everything related with noise. So they are also very well. They have very good performance, and they can be used for extreme climates, and of course there is an increased cost associated to the fact that we are dealing with a double stool wall, not a single stool wall. So regarding the fire resistance of light steel frame walls, there is the standard fire test, which is the EN European Standard 1363 Part 1, that specifies the fire resistance in 3 main domains. So it means for load bearing, integrity, and insulation. For this case, for a partition wall or non-load bearing wall, we should be concerned with integrity and of course insulation. And in this investigation, we are our main concern is insulation. So we are looking for the temperature evolution on the unexposed side of the wall, and we should track the value of the average and maximum temperature in this zone. And the criteria are, so we should look for time, the fire resistance time to reach an increase of 140 degrees above the initial average temperature for average temperature of the wall. And for regarding the max, we should look for an increase of 180 degrees above the initial average temperature. And of course, this wall is going to be submitted to the standard file ISO 834 that we have the very well-known equation and curve in this slide. So the main objective is to perform experimental tests to investigate the thermal behavior, of course, associated with the fire analysis of different kinds of configurations of double-stooled light steel frame walls, and to predict, of course, their fire resistance in terms of insulation. And of course, we are going to do or present experimental tests, but also present some numerical validation, and of course some other a new proposal for a simplified calculation method based on the improved design method that is that was originally developed for timber structures. So in this slide we can see the 8 specimens that we decided to test. So as you can see, the double-stood wall is going to be protected by one single layer in each side, which are the layers on the pink color, or double layer in each side, as you can see for specimen number 2. And the difference between the specimen 1 and 3 is that we decided to include some insulation material inside the cavity. So theoretically there is no void space in between the steel studs and tracks, of course. And then we decided to check what happens if we move the insulation for one of the layers of the stud. So if it is if the insulation material is close to the far side, or if it is close to the unexposed side. And we also decided to modify the number of studs that are close to the far side. So specimen 1, 2, 3, and 4 and 5 has 3 studs on the far side, and specimen 6, 7, and 8 we decided to put 4 studs on the far side. So the number of supporting points for the gypsum layer on the far side is going to change according to the configurations of the specimens. And of course we have on the right side a 3D virtual image of the stud wall, or double stud wall, and with every details regarding the connections and the screws that were used to fix the gypsum layers to the light steel frame. Here we have some specific notes regarding the fixation of the partition wall to the furnace, the frame of the furnace. And for this case of building elements, we need to fix 3 sides of the wall, and we have the right side is not fixed, so it's free. There is a gap of 25 millimeters, and then there is more information regarding the fixation of the light steel frame wall to the frame of the furnace. And this slide presents some details regarding the different types of thermocouples that we used for the experimental data acquisition. So we decided to use welded thermocouples to pick up the temperature on steel parts. We used the bed thermocouples. We decided to use 2. They are located in the fire exposed side, and they are going to measure the temperature of the first millimeter of the gypsum plasterboard that is exposed to the far side. We use also some twisted thermocouples to specific points inside the insulation material, and we use the plate thermocouples to measure the cavity temperatures, and disc thermocouples to measure the temperatures in the unexposed side according to standard. So we follow the standard to make the tests, but we also decided to use extra measuring systems to provide more data, of course, for the analysis and the investigation that we did. And of course, we also use infrared measurement from the unexposed side. We're using a machine located 3 meters apart of the wall. So here we can see the first experimental results. So we can see a picture of the infrared time-lapse, and of course we have the temperature evolution in specific points, and some of them are averaged already. So we we made a lot of measurements in the exposed stud, but of course for similar position we made the average of those measurements, and we are presenting, as you can see on the left graph, the ISO 834, the furnace, the true, and the theoretical. Then we have the exposed measurement, which means the average values of BT1 and BT2, the bad thermocouples 1 and bad thermocouples 2, and the hot flanges, the cold flanges of the exposed side, and of course the same hot flange in the unexposed side raw of the double wall. The graph on the right side is very important because it gives the information of the maximum evolution and average evolution of the temperature on the unexposed side, of course. And we have a mix of the average of DTs, and we have also the average coming from the infrared camera that we are seeing animated in this slide. So this is the end of this final state of the specimen number 1 from the point of view of unexposed side and exposed side. As you can see, on the exposed side we have very large cracks that allow the heat to flow through and gets inside the cavity, and some cracks formation, of course, on the unexposed side, as you can see on the left side. Those are the results for specimen 2. So for specimen 2 we doubled the number of layers of gypsum, as you can see on the bottom left of the slide, and of course the fire resistance increased a lot, and of course there is no insulation material inside the cavity. And on the right side we have two pictures in two different time instance, and we can check some important material degradation during the test. Of course, this is a picture from the inside of the furnace, not from the outside. Some experimental results coming from the infrared. Of course, this is the real image on the right side, and on the left side we have the real picture at the end. So, but this is the time lapse of the infrared. Of course, we have single images that are collected together to make this GIF animated picture. Specimen number 3, so is very similar to specimen number 1, but we decided to include some insulation material inside the cavity, and of course the fire resistance increased a lot. As you can see, some pictures on the right side about material degradation, and on the graph on the right side shows, of course, the same. So the average and the maximum temperature evolution of the unexposed side of the wall. So on the picture on the left side we have the final state of the specimen number 3, and the image on the right side we have time lapse for the infrared camera. So as you can see, of course, the crack formation on the left side agrees with the infrared image on the right side. We have the results for specimen number 4. So we decided to remove some of the insulation of the cavity and put the insulation material in the stud raw of the unexposed side, and of course there is no material insulation on the exposed raw, as you can see on the left side and bottom left side image. So we have the time evolution average, of course, for similar positions in several points, and of course the main graph regarding the maximum temperature and average temperature collected on the unexposed side of the wall. The results, the final results of the specimen number 4 and the infrared image. Okay. The specimen number 5, we decided to move the insulation material to the exposed side, and of course we got better results. So this is very important. This is a very important conclusion from our investigation. And the same, so some particular degradation material at an instance, and the average evolution of several points. And on the graph side, on the right side, we can see the maximum and average temperature evolution. The comparison of the final state of the unexposed side wall and time lapse for infrared measurement. You can see again we can follow the cracks using and comparing the cracks using the infrared. Specimen 6, we decided to move the position of to modify the position of the tracks. The number of tracks exposed to far side is now 4, not 3, and we can say that the plates on that side would have more supports from the point of view of the fixation. So we have the same, some points where the temperature was measured and averaged, and on the right side we have the most important parts, which are the max and the average temperature on the unexposed side, and the final results, of course, and the criteria to achieve the fire resistance. Some pictures and time lapse from infrared. Specimen 7, we decided to repeat the position of the insulation material on the exposed side, but this time, if you remember, the number of studs that are in the exposed side raw is 4, not 3, and some pictures from during the test and after the end of the test. And as of course, we can also take some nice graphs coming from several points on the left side, and on the right side we can see the evolution of the max and average temperature of the in the unexposed side. Some comparison between the final picture and the time lapse using infrared. And the last specimen is specimen 8. We decided to use the specimen without insulation in the cavity, and we decided to use 2 layers of gypsum on the exposed side and 1 layer on the unexposed side. This is not very common, but we decided to analyze the effect of using a different number of protection layers in both sides, and again the same types of results. And the final comparison between the final state of the unexposed side, and also the time lapse for the infrared. Okay. And finally, the conclusion regarding the fire resistance time from the point of view of average and max, and of course also the fire rating. So it means that we should look for the lowest time, and then include this lowest time in a scale that is specified by standard, and of course that will give this kind of solution, layer solution, the fire rating of each kind of specimen. So for specimen 1 we had We found 73 minutes to reach the criteria for average and 74 for maximum temperature. And of course, the fire resistance would be 73 because it is a hard condition. But if you need to make the fire rating, it should be only 60. It cannot be a different number. For specimen number 2, the value increased a lot, so we have almost 2 hours of fire resistance, but not exactly 2 hours, so that's why the classification is not high 120, but it is high 90 minutes. For the specimen number 3, as you can see, we reach 180 minutes, so it means 3 hours of fire resistance, because the T average was 190 minutes and the T max was 186, so the final time fire resistance would be 186, and of course 186 is bigger than 180, so it can be rated as I180. So, and of course for the other specimen 4, 5, 6, 7 and 8 we have the final results of the fire resistance. This slide starts the presentation of the numerical simulation. As you can see, we are going to use 3D models, so it means that we are going to use the finite element method to make the model, and we are going to use perfect contact between materials. So this is important, and it should be noticed because the fact of being in perfect contact may achieve or may get or may give us some small difference in comparison with the experimental results. Because it is a non-linear process, we are going to use convergence criteria, and it's going to be based on heat flow measurement. We're using a tolerance value of 10 power minus 3, and a minimum reference value of 10 power minus 6. And of course it is an incremental solution, and we are going to use a time step of normal size equal to 60 seconds that can be reduced to 1 second, and the maximum size should be or can be 60 seconds as well. On the right side we have some 3D meshes, as we can make a look on different types of materials and positions. So the purple one is the gypsum plasterboard, the dark blue is the steel frame. We have also some light blue for the head layer that I'm going to talk about, and the gray color is dedicated for the ceramic fire. So for this model we are going to use 2 different types of finite elements. We are going to use the shell to model the light steel frame, and this element is quadrilateral, so has 4 nodes, and each node can have several degrees of freedom because it is a layered finite element, and we are going to use linear interpolating functions, and we are going to connect the light steel frame with gypsum plasterboards, and of course also with the ceramic fiber, and also with the thin layer of air. And for these 3 types of material we are going to use solid finite element, which is a 8 nodes finite element with 1 degree of freedom per node, and this element also uses linear shape or functions or linear interpolating functions. Here we have we are presenting the boundary conditions. So we are following the boundary conditions proposed by or defined by Eurocode 1 part 1.2. Typically for this kind of tests we are going to use on the far side some convection and radiation. Convection using 25 coefficient, the convection coefficient of 25 watt per square meter Kelvin, and in both cases for radiation we are going to use the emissivity of the flames equal to 1, and of course the temperature of the gas is going to follow the ISO curve. So we are talking about boundary condition number 1. For the boundary condition number 4, that is specified in this same Eurocode, we are going to use convection with the convection coefficient of 9 watt per square meter Kelvin, and we are going to use the bulk temperature equal to the initial, so 20 degrees Celsius. So it is going to be the room temperature. So this 9 includes, is proposed by Eurocode 1 part 1, 2, and includes, according to this Eurocode, includes the effect of the radiation. Okay. So we have decided to use two other different types of boundary conditions, the number 2 and number 3, and of course this is some new boundary conditions that are not specified by any standard. So they were developed by ourselves, so we think that this works fine whenever you have a cavity that is not insulated. So you need to assume that it is also in the region 2 and 3 some heat exchanges or heat flow from using the convection and the radiation method of heat transfer. So we decided to add some additional boundary conditions that are based on the measured experimental temperature that we took from the experimental tests. We decided to use the plate thermocouples, and we are going to use the information of those plate thermocouples to be applied in the model, in the finite element model, and this solution works very well. And we decided to use intermediate values for the convection coefficient. So this is also very important, and this is not the first time that we are applying this type of boundary conditions, and they work very well. So this is our proposal to make this validation. Of course, for double walls, it was our first investigation, and we decided to add an extra thermal layer for this model, which is identified by the air layer boundary condition that you can see on the specimen number 4 and 5. And on both regions, we decided to apply a thin layer of 10 millimeters layer of thermal layer, if you want, using air. And this helps a lot to follow the history of the temperatures in the specific points of that we decided to compare with experimental results. And why it is not linear? Because the thermal properties are depends on with the temperature. So we have the temperatures coming from the gypsum and the ceramic fiber. You can see the peak values for the free water vapor and some other different types of water that is inside the gypsum plates. So those works very well. This kind of material properties work very well with the numerical model. Also, the material properties for steel. We took the thermal properties from the Eurocode 3 part 1.2. So we have the peak value for the specific heat that is related with the allotropic transformation of the steel. And on the right side we have also the air properties, the thermal properties for air that we are going to use in this thermal layer. So here is the first slide where we can make the comparison between the temperatures coming from experimental tests and the temperatures coming from the numerical simulations. And of course, for the unexposed side, we decided to use several points to make the comparison. So we have the points that are identified on the bottom pictures of the slides, and we have of course we have the possibility to take some average video results and the maximum results from the unexposed side. We have a time lapse for the animation as well. This is the time lapse coming from the numerical simulations for specimen 1. Of course, this is comparison for specimen 2. The results agree very well, as you can see. And the most important part is that is the boundary conditions, the extra boundary conditions that we decided to include. That's why we call it hybrid methods, because we are taking the experimental temperatures measured on the cavity zone. That helps a lot. And this is the same, but in this case using insulation material. Specimen number 4, we have the insulation material in the unexposed side, 5 in the exposed side, but only a row of studs, and the number of studs that are exposed are 3, not 4. After specimen number 6, we decided to modify the position of the steel structure, and we have 4 studs that are exposed to fire, 1 layer without the insulation material, and we have, of course, the comparison between the experimental tests and the numerical results, even for the average and max evolution on the unexposed side. Specimen 7 and specimen 8. As you can see, the results agree very well. So it means that the model is working very well, and one of the key points is, of course, to use this hybrid approach. And that helps a lot. Finally, some comparison between numerical results and the experimental results. So we have the errors, the relative error between numerical and experimental results, of course, okay? And we have very smaller errors in below 10%, as you can see. So because it is really a full investigation, so we decided to propose the new design method, because there is no design method included in Eurocode, and we decided to use the new proposal that is that was developed by Fanji in 2010, that is going to be included in the future version of Eurocode 5, part 1, 2. And based on that, we decided to propose a similar formula to find the fire resistance of any kind of those 8 specimens. And of course, this formula depends on the number of layers of protection that we have on the wall. So we have layer 1, layer I, layer n-1, and layer n. So layer n is normally well known by insulation, while layer 1, layer 2, layer 3, layer 4, and layer n-1 are very well known by the name protection layers. So the final, the fire resistance is going to be the summation of the protection of each layer, and we decided to propose some modifications with regard to this improved design method proposed by Fanji, and those are identified in this slide. So we decided to make the correction, coefficient correction for the position coefficients. So we modify from 1.6 to 3.2, which makes sense because we are talking about double stud walls, and some other modifications on cover position for the exposed side to increase the results. Of course, there is also another factor that is called delta T, which is a kind of compensation for the proposals that are presented for the cover position coefficients. Okay, so now we have the results coming from experimental tests, numerical simulation, and simplified, and we have the difference between experimental results and simplified method and numerical results and simplified method. And the difference is they are very, very good. So that's why we think that this proposal is good for to be included as well in the future version of Eurocode 3 part 1.2. Finally, some conclusions. I would say that we develop an experimental numerical investigation of different configurations for double-stood light steel frame walls, and we try to find the fire resistance. We also present a comprehensive numerical simulation that was used to carry out to validate the model, and we also identify some important parameters for the simulation, and I call your attention to this hybrid approach, which really helps a lot, because it's the only way to get particularly the events that we are expecting due to the damage of the materials. So this new hybrid method is good for that. So we are going to prevent, we are going to achieve or to find the effects of cracks, falling offs, and openings. We assume the perfect contact, and of course this is a potential source of error in the numerical model. And a simplified approach was developed, which is innovative. There's an innovation in this investigation to get a simple way of finding the fire resistance of this kind of walls. The experimental tests show that a wider cavity is beneficial to the thermal insulation behavior of light steel frame walls under fire, reducing the heat rate to the unexposed surfaces. The position of the cavity insulation greatly increases the fire resistance of the wall. So if we put the ceramic fiber in the unexposed side, the fire resistance of the wall increases. When the cavity is fulfilled with ceramic fiber, the fire resistance of the wall increases by a factor of 2.6 when compared with the assembly with the void cavity and with the same number of gypsum plates. And when the insulation is in contact with the light steel frame, the heat builds up, of course, around the hot flange and of the steel studs, and increasing the heating rate of the steel sections. And placing the insulation towards the unexposed side of the plasterboard is detrimental, as we saw. And when the insulation blanket is placed towards the exposed side, the fire resistance of the assembly increased by a factor of 2.6 when compared with assembly with the void cavity, which is similar to the fire performance. And using 2 gypsum leather plasterboards on both sides led to an increase of fire resistance of the assembly by 60%, while the employment of a double gypsum panel only on one fire side gives an increase of 40%. Finally, I would like to say that there is a good agreement between numerical, simplified, and experimental results. This ends my presentation, and I will be delighted to answer to your questions. Bye-bye.